My name is Risa Fury. I am the Director of Marketing and Communications of the global mining sector at Stantec. And it's a pleasure to chair this session. My co-chair didn't make it, unfortunately. I'll say a little more about him later. I want to start with a safety share. So I think everybody knows all about the Heimlich maneuver. I almost called it the remover. This is the universal sign that you're choking. And if somebody needs the Heimlich maneuver, you take a fist, you go from behind, a little above the navel, and then you sort of push up. And the reason why I bring this up is because I was working at home one day and I got a little shaky and I needed some protein, so I took kind of a spoonful of peanut butter and got to the point where I wasn't getting air, and it was really the scariest thing that has happened to me in a long time. The things that went through my mind was, who is going to help me, and can I run to the neighbors before I pass out? And then I realized I needed to know how to do the Heimlich maneuver on myself. So it's the same procedure. With the fist a little above your navel, and then you would go to a chair, or better yet, a countertop, and then you can try and dislodge what's happening. Most importantly, you want to probably just not take such a big spoonful of peanut butter. This is my co-chair, looking very formal, and I want to thank him because he did a lot to make this session one with a lot of rock stars in it. So I'm kind of excited to get started. The goal of the session is to understand why and how to take a holistic approach to water and mine water systems. And the reason for that is just because globally, organizations understand that this is a competitive advantage if you take this integrated approach. And it helps you gain financial and public support for your projects. Our next speaker is Marcelo Reginato. He is a water resources senior engineer with Jacobs. He brings 20 years of experience in systems models, watershed modeling, hydrology, hydraulics, and water resources, besides being the technical lead in the development of several water balance models in the mining industry. He has been a key technical resource on many high-profile conservation, groundwater recharge, and restoration projects. His principal technical expertise is in systems models and water resources. He has an MS in civil engineering from the University of Nevada, Las Vegas, and a BS in civil engineering from Universidade Estadual de Campinas, Brazil. Welcome.
Thank you, Risa. Thank you all for joining this session this morning. I would like to begin to say thank you to my co-authors, Jim Stefanoff and Rob Reisinger. Title of my presentation today is the Water Balance Model Benefits and Results During the Reclamation Phase of a Mine. So I'm hoping that by the end of the presentation you will have a better idea of what is a water balance model and how we use a water balance model to make decisions at a specific site. So my presentation has two parts. The first part, I'm going to give you some basics of water balance models, how we use that water balance tools to make decisions. I'm going to go through some of the model development steps and some typical activities that can be we could use the model to make good decisions. Then the second part of my presentation, I'm going to talk about a case study. So I have three examples that I will present, and those examples are for the reclamation phase of a mine site. What you're going to see is that what the model was predicting compared to actually what happened at the mine. So we'll give you an idea of how we use the model for that site. So let's start with the phases of a mine. What are the typical questions that a manager might have during the different phases of a mine. So we have the development phase, we have the production phase, and the reclamation phase. And during all these phases, the water balance tool can be really helpful. So I have a couple bullets as examples for each one of the phases, how the water balance model could help you. So for the development phase, you might want to try to understand how reliable your water source is. So you're probably going to need some water in your mine, so you want to understand how reliable and where the water is coming from to your site. You might need to do some stream diversion. So the model might help you size that diversion that you need at the site. Then you go to the production phase of a mine. A model could be used there to dealing with the production of the mine. So you might start with one idea of what will be your production, but then what happens if you change your schedule, your production schedule of your mine? Do you need more water? Where are you going to bring that water from? How much water are you going to import? You probably will have to, you will need a treatment plant. So can we design that treatment plant for the production phase and also for the reclamation phase? That's another question, so that the water balance could help you there too. And then finally, we have the reclamation phase of a mine. And so questions at how the water management will change from the production to the reclamation. If it's an open pit mine, you will have your pit filling with water, so you might want to manage that water level. That's a question. And the water treatment, you probably will have to treat some of the water, but for how long, and what are the options you have on your mine? So this is a few examples for the different phase of a mine, how a water balance could be helpful. Specifically for the reclamation, because my case study will be focused on the reclamation, so I wanted to give you a little bit more detail on that. What are the typical activities that you have in a reclamation phase of a mine? So first you want to understand the sources of water contamination at your sites. You want to avoid hot spots, so you want to keep your clean water clean. You might want to do some stream diversions for that, reroute things at your sites. You might want to put some waste rock covers, so you understand the effect of the covers downstream on your flows and water quality. You might have some passive or active water treatments, so how that works with the entire site. And also, you will have some, probably a pit lake that you need to manage the water level. So some example of activities in a reclamation. So the water balance provides a lot of value when you try to evaluate multiple reclamation options that you have. So you run the model with what if cases. What if I have this project? What will be the impacts downstream on flows and water quality? Water balance also can provide some insights on the most efficient alternatives, where you're going to get the most bang for your buck, right? Where you want to design, actually implement projects. And it can help also evaluate the uncertainty that you have in your site. Uncertainty could be from water quality, concentrations that you might be seeing at your sites, or the uncertainty related to the activities you're planning to implement at your sites. So a little bit about the water balance components. So first you need to define the boundary of what you're going to model, right? And here we first delineate what you're going to, that's the model domain, what you're going to include in your model. Once you define that, you want to understand the inputs to your model, where the inflows are coming from. So in this cartoon example, you might have some in-stream flow here, another stream flow here. You might have some precipitation, maybe some groundwater. So that's the water. You might have some loads too coming. You might want to keep track of the loads also coming to your system. So you're going to have some water quality, so you can keep track of the loads coming to your system. So you got the inflows. You also want to understand what are the outflows from your system. So in this case here, we have the outflow coming right here. You might also have some groundwater. Of course, you have some evaporation. You might have some groundwater outflow from your system. So once you define the boundary, you know the inflows, you know the outflows, then you need to keep track of the changes in storage within your boundary. So that's in a nutshell what we do in water balance tools. And we have different components. So we have a pit lake, we have waste rock dumps, we have rerouting of streams, treatment plants. So the water balance tool will connect all these elements under one umbrella, under one tool, and then you see how one affects the other. So let's talk a little bit about the development. How we develop these tools, these water balance tools. So going from the site, we define a conceptual site, how we think that the water moves through the system, and then the model. Our approach generally is a top-down approach where we start from simple assumptions to complex. And that's dependent of the data we have and the questions we want to answer. And the challenge here developing these models is to match the appropriate level of detail with the data we have, okay, and the model requirements. That's the key thing. So we want to look at what information you have, what data, what you understand about your sites, and then build the model that is that matches that. I think there are like two main cycles when we develop a model like this. We have start with the conceptual model. We see what kind of available data is out there. We try to fill data gaps, collect more data gaps, and then we reach a better understanding of the sites. And we can keep doing this. We can keep collecting more data and improving the site understanding. And then there's a model usage cycle. So once we are ready with the conceptual model, we know how the system, we have an idea how the system works, we can start developing the model. Then we can create scenarios, we check model results, we hopefully answer the questions. And there might be some more questions after we run this first cycle. But every time we run this, we improve a little bit more of the model capabilities. Also, the insights we can get from the cycle here might improve our conceptual model. And then we might have to request more data, see if we have more data, and run through the cycle. So this could be a week effort. It might be a very simple system that we have data. We're not going to collect more data, so we know exactly what we're going to do. So we develop the model in a week, 2 weeks, or it could take many years, depending on how many questions we want to answer, how much data we want to acquire. So with that, I'm going to start the second part of the presentation, where I'm going to talk about a case study. So this is a historic mine, and the operation ceased in 1986. There's some reclamation that was done back in 2000, but most of the reclamation activities happened after 2014, about that time, more recently. My case studies will be, I have 3 case studies. One, I'm going to talk about waste rock cover implementation. The second, stream diversion. And the third, lake stratification. So here's the site. The drainage here is from north to south. There are 2 watersheds. There's some waste rock piles here and 2 main peat lakes. So a little bit more about the site. So here you can see the watersheds in color, the green and the yellow, the 2 main watersheds we have, and approximately the drainage with the acreage, just to give you an idea of the size of the project. We have about 55 inches per year of precipitation at the site, so it's not a dry area. Have a good amount of rain. And the drainage coming from north and from pond 2 goes into pond 1. And out of pond 1, we discharge into the mainstream. The flow here is about 850 GPM per year on average for this watershed, and 150 GPM, gallons per minute, for the smaller watersheds. So the precipitation is the main input to our model. And when we start developing this tool was about 2014, 2015. We had some historical precipitation. That's what this chart is showing. So historical monthly precipitation. But after that, we didn't know, okay, how much precipitation we're going to get. So that's why you're seeing this chart here. Sometimes we might have a very dry month or very wet month. This was based on historical precipitation. We had about 50 years of precipitation records, and we used that in the model, trying to understand our uncertainty related to the hydrology. So this, the first case study will be at that watershed, waste rock covers. The second case study, stream diversion up on the north area. And I'm going to talk about stratification on case study 3. So first one, waste rock cover implementation. On that area, what's happening here, we have the watersheds. The water infiltrates, hits the contact, the spoils, and we have some flow and water quality downstream here. So the idea was to put covers there to avoid the clean water from precipitation to reach the spoils and improve the water quality of seepages that were daylining down here. So the idea with the covers, after the covers are done, we collect the clean runoff, and that will help the dilution with the seepage we're seeing here. So the question for the model was, okay, if we put those covers, what will be the impact on the seepage down here and the water quality? The challenge here was to make a model flexible enough to accept inputs so we can change the size of these covers and change assumptions and see what would happen downstream. The outcomes of the model, we run a series of scenarios, is that we change the size of the covers based on what we're seeing from the model. So here some other results. This is the estimated seepage at the bottom of the hill outflow without the cover improvements. So here's what we are expecting in flows from the sites from 2015 going forwards. That's the range of flows we were expecting depending on the precipitation. So we run this scenario without the covers, and then we put the covers in a model when we saw the impacts that the covers would have in the flows. We also did this for water quality. So the covers were implemented in 3 phases, first phase, second phase, and third phase. And you can see here that's the significant reduction on the seepage. Remember, this is not the overflow, the runoff. The runoff was diverted. This is just the seepage. And then we verified with measured data. So the black line here was actually measured seepage flows at the sites. So we had a little bit of data from 2013 to 15. So we used this data to calibrate the model. And this here was the range we estimate in reds, and the black line was actually what we measure at the sites. So it was, we're really happy with that correlation. Sorry. So we go to the second case study. Stream diversion was up north. The challenge here was we had some waste rock located at this part of the watershed. So this is the watershed, some waste rock. And what we had some clean water from this blue zone going through the waste rocks, and the water quality downstream was poor. So the idea here, if we implement collection, if we divert the stream, we put concrete channels here to keep the clean water clean downstream and help dilute some seepage, what would be what the model will tell us. What will be the benefits of doing such project? So here, similar to the previous case study, but here I'm showing now metal concentrations. So we had a target goal for concentrations downstream. Here, by the way, is measure concentrations at the reds location here, from here. And you can see the concentrations for the metal really dropped after the project was concluded. So we have the conclusion of the project there, and the concentrations from around 0.06, it dropped between 0.02 and 0.04. This was our goal. Same idea with the precipitation uncertainty. We try to cover that. The blue dots here are the measured concentrations. I just added a moving average line here just to help see it as the difference between the model versus the observed. Now the gray line here is a scenario that it's a no action scenario. What would happen if we didn't have these stream diversions? And with the precipitation that we saw at the site, we would see higher concentrations. So then we go to the next case study 3. That was the lake stratification. So the question here was, with all the benefits we did upstream, plus some benefits, some reclamation activities we had at the watersheds, what will be the water quality discharge from the pit lake? So that's what we were worried about. We start with the big picture. Remember the top-down approach. And first we had this pond as one bathtub. And that wasn't a very good approach. It was too general. That's the top chart here. I'm showing you the metal concentrations. Measure is the green line. Measure is the green line. And what the model was predicting was the red line. So not very good correlation at all if we consider a one bathtub. So we had to, if you remember the cycles I presented in the previous slide, we had to adapt, change our assumptions, collect some more data. And the assumption how we changed this, we had now our lake is split in two zones, the epilemian and hypolemian. And when we did that, we had some logic moving load from those two zones. And as you can see here, really improve our metal concentration compared to what we're measuring. Again, the green line here is what was measured, and the red line what the model was predicting. So just to conclude, a summary. Hopefully I gave you a little idea of how we use a model, a water balance model, how we develop. I think there are several advantages of having a model available for your site. First, while you develop the model, it improves your system understanding. Because you're going to get all these scattered data you have, data, operations, you're going to put everything under one umbrella. It will help you a lot, the site understanding. It's a tool that facilitates the decision making. Once you present model results in a consistent way, it really facilitates the decision making process. You definitely better allocate your reclamation funding. You're not going to build everywhere. You're going to see where it makes sense to have some projects implemented. And finally, that's the most common benefit of a model is the forecast reclamation benefits, what I was showing to you. Most of the time, people think about this here, the forecast of reclamation benefits, as the only benefit of a water balance tool. I just want to highlight the first one here, the system understanding. That's a really valuable benefit we get from developing a water balance tool. That's all I had to present today. With that, I'll see if I have any questions.
We don't have time for questions.
Oh, we don't have? Oh.
Do you have one? Is it quick? Can it be quick? Yeah.
Yeah.
So your waste talk scenario, did you have it linked to some sort of Hybris
No, no. There was a question if we need a groundwater model to do that, right? But we found good correlation with the assumptions we had, so we didn't need that. But oftentimes, you're right. Sometimes on the cycles, you found that, okay, I need a more detailed model, and then you go and you create a more detailed model. If you had any more questions, I'll be around, so please contact.
Thank you, Marcelo. Our next presenters are Barb Nielsen and Leonard Stenban. Did I get it right? Barb Nielsen is a geological engineer and has over 32 years of permitting, characterization, and remediation experience on a variety of sites. She began her career as a regulator in South Dakota and progressed to managing several groundwater protection programs. For over 13 years, she has been the manager of remediation projects for Freeport-McMoRan in Phoenix, Arizona. Several projects that she has managed and several projects that she has managed and have received state and national honors. Leonard Sen, and I worked on this. Dr. Leonard is a respected research scientist with over 20 years of academic and professional experience working across multiple disciplines within the field of biology. He has worked with Freeport-McMoRan's environmental technology team, an internal research and development group for over 5 years, and leads the passive bioremediation and phytotechnology programs. Welcome to you both.
Good morning, everyone. How are you? We did a talk previously today that was more about, the characterization of the entire site. We're not going to do that here, but so what I'm going to do is I'm going to give you a little backdrop of what's going on, and then Lenny will take it on from there. These are some of the people that were involved in the project. As we said, this is a former vanadium mine near Rifle, Colorado, which is on the western side of Colorado. It was operated intermittently between 1929 and 1975. It was never operated by Cypress Climax Metals Company, who is a wholly owned subsidiary of Freeport-McMoRan, but Cypress did lease it out to numerous other people. Just a map showing you where the site is relative to Rifle, Colorado. Some of the features at the site, there were 6 mine openings, 5 adits, and 1 suspected collapsed shaft. 2 of the adits discharge. You can see the discharge is not very much, 1 gallon and 2.5 gallons. There was 2 waste rock piles, but the main waste rock pile was 17,600 cubic yards, so very, very small site. And the site had debris all over the place. I mean, the kids had even drug a couch up into one of the adits. It was pretty interesting. So we could tell that there had been a lot of trespass or recreational use of this site. And there was also an unimproved road on the site that actually the Forest Service did use here a few years ago for fighting a fire. We entered this site into the Voluntary Remediation Program with the state of Colorado. And if you don't know much about the Voluntary Remediation Program in Colorado, the way it works is you go out and you do your work, and you kind of serve it up on a platter to them, and they either say yay or nay. But because this site had a radioactive component to it, we also we're visiting with the radiation unit, and we got the voluntary program to buy in to take this site along like you would normally take it along and give us approvals of work plans and stuff as we go, so that when we do get to that end point, we've already got the yay. So that's kind of what we did. So you can see we characterized the site. We closed the openings at the site. We improved the fire access road. We regraded the main stockpile. The other one, from a risk perspective, was there. We didn't have to do anything with it. So, and not only that, it was very dangerous to try to touch it. It was hanging on the side of a very, very steep slope. And then we covered that pile with an infiltration barrier and a rock cover. And the main reason we chose the rock cover was a couple different reasons. Even though we didn't necessarily need to do it from a risk perspective, rock provides shielding, right, from radiation. So that was one reason. But more so than anything was it's very difficult to get anything to grow in this area. So the rock cover pretty much just makes it blend into the rest of the hillside. We also installed a stormwater diversion system as well. And in May of 18, we got a no action determination from the Voluntary Remediation Program. However, one thing that the voluntary program does not cover is surface water discharges. And we had those two adits yet to deal with. Now, they wanted us to look at actually getting a permit. We didn't want to get a permit because we could never saw the discharge leave the site. The discharge would infiltrate into the ground not very far away from the adits. So hence the reason why we wanted to look at doing bioremediation at this site to eliminate those discharges and to avoid a long-standing permit. A couple things that are interesting, not really relevant to this talk, but interesting, is the adit discharge when compared to the groundwater chemistry at this site was different. They're different types of water. And not only that, but the groundwater was a magnitude of order higher in uranium concentration than the adit discharges. But still, when you compare the adit water discharge to surface water standards, you can see that there's numerous standards that we would be exceeding, like selenium, total uranium, gross alpha, gross beta, radium, and so on. So hence the other reason for a bioreactor. And with that, here you go, Lenny.
Close enough. Thank you, Barb. And it's Santi Esteban for anyone who's interested. Okay, so we were interested in implementing passive biological remediation. And those of you that are not familiar, it's just basically a catch-all phrase for a range of technologies that emphasize biological activity, microbes, plants, etc., that do the lion's share of the remediation work for us. And so we found that it was particularly advantageous at a site like this because this is a legacy mine site, remote, and lacking infrastructure, and so it offers lots of advantages over other technologies. We're relying on utilizing natural organic substrates, microbes, and therefore they generate relatively less sludge than active water treatment. We've got relatively lower operating and maintenance costs and minimal energy consumption. In fact, the entire system here is operated by gravity flow. There are, of course, limitations. It's not a panacea. We are limited by microbial performance and potential toxicity with high metal loadings. So that all has to be factored in. There very well is seasonal variation in performance, particularly in cold climates, such as this site in western Colorado. And often you're really confined by space, because these systems, being passive and relatively less efficient than active systems, do require a large footprint. Okay, so a little bit of background on the system that we settled on. We decided to use a sulfate-reducing biochemical reactor at the site as one component. And essentially we're focusing on sulfate-reducing bacteria, which are utilizing sulfate. And they are reducing that sulfate, producing hydrogen sulfide as a byproduct, and that then combines with cations in the water, forming metal sulfide precipitates. Now, they're also generating alkalinity in the process, which increases the pH of the water. And in terms of a carbon source that they require for electron donors, we're utilizing locally available organic substrate materials to support those bacteria. And sizing of these systems is based on oxygen, metal, and sulfate loading rates. And so those are all factored in. And for this system, we're thinking ideally, a hydraulic retention time of 30 hours. So we began working with Golder throughout this whole project, but Golder did some bench scale evaluations with the objectives of showing that we can utilize this technology for bulk removal of those constituents of concern, sulfate, selenium, zinc, uranium, and then some of the radionuclides. And this would then be used to provide a design basis for a full-scale system, particularly factors related to size of the system, flow rates that we'd be able to handle, and hydraulic retention times. So the lab scale evaluation looked at using two biochemical reactor columns and a mixture of Adit seepage from both sources, and then two different recipes here, really focusing on changes in wood chips, the relative proportion of wood chips and sawdust as long-term carbon donor sources. And then operated in downflow mode, and they were metered, and then monitored influent and effluent concentrations for several months. Just to give you a sense for what we're dealing with: sawdust, wood chips, sheep manure as the inoculant, the original source of the sulfate-reducing bacteria, hay, and limestone for some additional alkalinity. And here's the setup in Golder's facilities. And this is what we found. Influent sulfate concentrations here in blue, and there were multiple phases of this study. The first phase was just Adit 2 water, and then a blend of Adit 2 and Adit 1 waters, and then a different blend, different proportions, to see how performance might change depending on the relative contribution of the Adit waters to a full-scale treatment system. And so these are effluent concentrations in the two columns for sulfate. So we had pronounced sulfate removal. Same with selenium, really good results. Uranium, and uranium is reduced in this environment and removed. And then radium, and then alpha and beta. So really happy with the results. Found over 90% removal, upwards of 98 to 99% removal, sometimes 100%, depending on the constituent, down to below method detection limits for several of them. And then looking at sulfate loadings, we estimated that a full-scale system should survive in 15 to 25 years. Okay, so then using that information, we developed a design basis for a full-scale system. Again, working with the state and the treatment objective of bulk removal of those constituents. Same ones we were dealing with in the lab evaluation. We needed to provide year-round treatment of this Adit seepage because the adits were constantly flowing at varying rates, but the site being at 6,000 feet elevation does get very cold, but we needed to be sure that we could design the system so that the bacteria were maintained in at least operating conditions in an environment where they could continue reducing that sulfate year-round. And we also didn't want to have any issues with any of the pipes freezing during the winter, so we incorporated that into our design. And then lastly, we wanted to ensure that we had non-point discharge of the treated water. And I'll show you how we managed that. Okay, so here's a view of the sulfate-reducing biochemical reactor, the full-size system. We designed this for an HRT of 32 hours. It was downflow, and this is about 4 feet deep of organic substrate. And we had a water level control unit over here downstream, so we could always maintain water levels within that system. And this was roughly 1,350 square feet in size. Like I mentioned, we use locally available organic substrates, wood chips, limestone sand for that alkalinity, some hay for more readily available electrons for the microbes, and then the original source of the sulfate-reducing bacteria in the sheep manure. We covered it with an insulated cover to help control temperatures throughout the winter. And then we finished construction of this system in the fall, filled it up with Adit water, and within 2 weeks, we saw strongly reduced conditions within the bioreactor. So we started operating it throughout that winter. Okay, then we added, we didn't evaluate this in the lab, but we added this in the full-scale system, a aerobic polishing cell. In this case, this is a vertical flow wetland. And the way we design this is that it distributes water across a vegetated sand bed, and this allows the bioreactor effluent to be distributed into the system, and so it's insulated throughout the winter to ensure that the effluent does not freeze. And then that's overlying a gravel layer, and so this is downflow percolation of the treated water. As it passes through the root zone, this is where the phytotechnology aspect comes in. It passes through the root zone, you've got additional biological treatment as well as physical and chemical processes that are doing some final polishing on that treated water. And this was sized based on the total suspended solids loading rate that we were expecting into the system. We needed about 1,000 square feet of area, and we incorporated this by constructing 2 vertical flow wetlands, and this is what they looked like. So we'll start from the bottom. This was unlined below, and we had a gravel bed, about 6 inches deep of 1.5-inch stone. On top of that, there was a 12-inch layer of 3/8-inch stone. Above that, 12 inches of sand, and then we covered that with 6 inches of mulch for thermal insulation. The bioreactor effluent was distributed in the sand layer to ensure that it wouldn't freeze throughout the winter. We salvaged cattails that were growing outside the adits, so these were already acclimated to that water chemistry. And then we sourced plants from local Alpine-Eco, local nursery, sourced 5 additional native species that we planted into the system, and we planted a total of 500 plants within these vertical flow wetlands. Now this is what construction of the site looked like. This is the bioreactor itself. We had a very small footprint to work with, so a very limited area, but things were tight. And so that actually led to a lot of interesting construction activities and managing the construction safely. This is the bioreactor. Here's the lining. Here's the effluent collection system within the bioreactor. Here's the distribution of the gravel layer at the bottom of that bioreactor. And then the organic substrate here. Just to give you a sense for scale and the mixture of that organic substrate. And then this is what the finished product looked like and the thermal cover on top. The aerobic polishing cells were originally planted in June of 2017. We ran out of time after the bioreactor was constructed in fall of 2016, so we had to wait until the next growing season. And then we provided water to help promote downward root development so that they could then utilize the bioreactor effluent. And within a few months, we had really excellent growth responses. This is an overview of the site. After construction, here's the bioreactor. The adits are right around here, and so water was collected from the adits, fed into the bioreactor, treated, and then distributed equally, or as equally as we could, into the 2 APCs on either side. And here's another overview. Okay, so these are some of the results from the bioreactor. Unfortunately, we are unable to collect samples from the APCs themselves because there isn't enough water being collected in the sampling system that we set up. So we can only rely on bioreactor treatment results. But we are having good removal here in the top line, the reddish brown line. This is the influent concentration for the next several slides, and then the green line is total and dissolved effluent concentrations. So we're finding good uranium removal, good selenium removal. Still trying to figure out what's going on with these analytical results from the lab. Zinc removal as well, and then gross alpha and beta, radium. So these are physical-chemical parameters. Adit seepage, this is far more circumneutral than the waters that we typically work with. at some of our sites, so this was sort of a nice change of pace. But you can see we're having really great change in redox conditions within that bioreactor, which is what's required for sulfate reduction and uranium reduction, and selenium as well. Obviously, dissolved oxygen is being consumed in that system, and then we're generating lots of biological oxygen demand because of that biological activity. So as of late, flow rates range between 1 and 2.5 GPM, and ORP, DO, and BOD indicate very strong anaerobic conditions, which is what our intention was. And we do know that BOD, ORP, and DO will be improved as that bioreactor effluent moves through the vertical flow wetlands, through the APCs. And we've learned that that's been well documented in literature as well as in other treatment systems that we've evaluated in the lab using that technology. And we have been able to show that microbial activity persists through the winter, even though influent water temperatures are less than 5 degrees Celsius. That's well below what sulfate-reducing bacteria typically prefer, but they're doing well under those conditions. These are average removal rates for some of the constituents. We are achieving bulk removal as intended to varying degrees. And this discharged water, after it passes through the entire system, does percolate down through the APC, so we have non-point discharge, but it does further improve the groundwater quality. So we did find run into some operational issues. We tried to implement these inline flow meters, and we just underestimated how much organic was going to be coming out of the bioreactor, so these things clogged up quickly. We tried to implement them to get a better sense and balance flows between the two APCs. So we ran into problems there our first winter, and so we had to come back in during the spring of 2017 and pull them out and add an overflow bypass. But we have achieved zero discharge. And this is just a photo of some of that work that was done to remove the inline flow meters. Okay, so in summary, we did meet all of our remedial action objectives. We treated the added discharge, managed it. We're finding the bulk constituent removal, no discharges, as well as due to the reclamation efforts, the site has been cleaned up, stockpile was regraded and covered, and managing stormwater successfully on the site, and ultimately protecting human health and the environment.
Great.
And so this is the end product. There you go. So I'm happy to take any questions. Please.
So you give it a 15 to 20-year life, something like that. Are there contracts in place to muck that thing out when that's done?
It is still our property, so that is something that we would do. We continue to monitor it, and so that's something that would have to be done at some point in time. Yeah. Yes. Back.
Sorry, I missed your no discharges point. I know there's water coming in. Where's the water going?
It's percolating down through the APC into the stockpile. So there's.
I mean, it must go somewhere, right? More water's coming in.
Well, the point is the reason for the natural infiltration is like I stated earlier, the groundwater quality is actually magnitude order more than what's coming out of the attic.
Okay.
So the theory is we're treating what's coming out of the attic because it exceeds surface water standards, but what infiltrates is actually improving the water quality
Right.
of the groundwater.
But it's true to say you're not storing all the attic water coming
No.
into this
No,
facility.
we're
It
not
goes
storing.
somewhere.
No,
Okay.
no,
But we're not calling that.
No, it's rock, the
distribution.
APCs are rock bottom, so
Okay.
it infiltrates.
Yeah, there's no surface water
Just
discharge.
wanted to clear that up.
Yes, absolutely. Yes.
The material that you're going to have to remove in 15, 20 years or whatever, it's going to contain a lot of uranium and radium.
Potentially.
What are you going to do with it?
Great question. We'll manage it obviously accordingly to, it would be thoroughly characterized and then managed as needed.
Okay.
Yeah.
Okay.
The knock on wood chips and other materials of that sort, long term, has been that you get a wonderful performance for a while, and then it falls off the table.
Right.
While typically in other projects, physical, not in South Africa, means 1 to 5 years.
Right.
Did any of your testing address that problem?
The lab scale testing for this project wasn't geared to that. It was too short term. But we've been evaluating sulfate-reducing bioreactors within our group since 2009. And so we have long-term data from lab scale and full-scale systems that we've utilized to get a better understanding of that. And so we try to plan accordingly and expect that you're going to have that drop off and you're going to achieve a lower steady state condition than what you'll have at the outset. So we do work with that and keep that in mind. Absolutely. Yes.
With the metals staying in the sludge, you're not mucking it out till after that 15-year period. Are you looking at the possibility of some of those metals redissolving as you had before?
They won't as long as water chemistry doesn't change dramatically. If you maintain anaerobic conditions in that system, they will remain as metal sulfides. Right.
The selenium and the zinc will stay in that.
Correct.
Everything stays in that.
Everything stays in the bioreactor, correct. And some residuals will even end up in the APCs where there's additional removal mechanisms going on. It all depends on the element. Yeah.
And in addition to doing influence and effluent sampling, you're also doing core samples of the material to see how it's performing.
Correct. And how it's degrading over time. Yeah. Thank you, Kim.
Great.
Thank you very much, everyone.
Thank you very much.